Hello friends, today we are going to discuss a problem based on conservation of linear momentum and position of center of mass. Let me define the problem and then we will discuss the details and the basic concepts which are required in order to understand and solve this sum. This is a boat which is 1.5 meter long. On one end of a boat, there is a boy is standing who is weighing 60 kilograms. On the other end, a girl is standing who is weighing 50 kilograms. The weight of the boat is 30 kilograms. Of course, the boat is on the water. The question is, find the distance through which the boat moves as the boy and girl exchange their positions. That is, when the girl walks over and takes the position of the boy and the boy walks over and takes the position of the girl, we are supposed to find by how much would the boat move. Now please understand, this problem can be solved by two ways. Number one, by considering the concepts of center of mass. Number two, also by considering the concept of conservation of linear momentum. We will discuss both the aspects today one by one. In order to apply both these concepts, the first thing that we must make sure is that no external force is acting on the body. So if you look at the boat and the boy and the girl and the system together, there is nothing external acting on the system. It is simply the girl exchanging position with boy and the boat is moving during the process. There is no external force acting. And when there is no external force acting, according to the first concept here of center of mass, we can say that the position of center of mass does not change. Let me repeat. When no external force is acting on a system, there is no change in the position of center of mass. Let us use this concept to find the distance through which the boat moves with the positions exchanged. And then we will come to the concept of conservation of linear momentum. So, part 1 is, we are going to consider that there is no change in center of mass and we are going to find the distance moved by the boat during the exchange. Let me redraw this as a system of particles. There is a mass here that is 60 kg. There is a mass here that is the mass of the boat, which is 30 kg. And there is a girl here whose mass is 50 kg. Let us work in centimeters. The whole length is 1.5 meter. The center of mass of the boat will act exactly midway. So it is at 75 centimeter. Let me consider this as the axis of reference. Let me take this as origin O and then I will try to find the center of mass with respect to origin O. So what is the formula of center of mass here? It is m1x1 plus m2x2 plus m3x3 divided by m1 plus m2 plus m3. Let us see the first situation where boy is here and the girl is here. Mass of the boy is 60, but its distance from the origin is obviously 0. This is 30 kg at a distance of 75 centimeter, and there is a mass 50 kg at a distance of 150 centimeter divided by 60 plus 50 plus 30. Let us see what we get here. What we get here is 30 into 75, that is 2250 plus 50 into 150, that is 7500 divided by 60 plus 50 plus 30, that is 140, and that gives me 9750 upon 140, that is 975 upon 14 centimeters is the original position of center of mass. So what we have computed here is the original position of center of mass with this situation, which is 975 upon 14 centimeter. Let me mark this as x1 and let me put it over here for our reference. We have obtained x1 bar as 975 upon 14 centimeter. You can take a look. M1 x1 plus M2 x2 plus M3 x3 upon M1 plus M2 plus M3. Now let us consider the revised situation when the 50 kg mass comes here and 16 kg mass goes on the other side. So if I redraw the situation here, what I will get is, there is a 50 kg mass here, there is a 30 kg mass here. This is after the system has shifted, but still the relative distances are not going to change. And there is a 60 kg mass over here. This distance is again 75 centimeter. This is also 75 centimeter. So let me find the value of the new center of mass, say x2 bar. Again I will use the same thing. M1 x1 is 0, M2 x2 is 30 into 75, and M3 x3 is 16. 75 to 75 is 150 divided by M1 plus M2 plus M3. Let me see what we get here. We will get x2 bar as 30 into 75, that is 2250 plus 60 into 150, that is 9000 upon 50 plus 30 plus 60 is again 140, and that gives me x2 bar as 11,250 upon 140. If I divide by, cancel out 0, I will get the new position as 11250, sorry, 1125 upon 14. This is the new position of the center of mass. Please see that as x2 is greater than x1, the center of mass has shifted to the right. But according to the principle that there cannot be any change in the center of mass, the entire system will move to the left by same distance, so that the center of mass again remains constant at the original position. So according to the new situation, the center of mass is this. But as we know that there is conservation of linear momentum, there is no external force acting on the body, so center of mass cannot shift. That is why, suppose the original center of mass, which was at a distance of 975 upon 14, and in the new situation it is shifted here by 1125 upon 14. In order to maintain it here, the entire boat will shift to the left through the distance of this minus this. So what is the total distance through which the boat has shifted? Now we can calculate it as x2 minus x1, and that gives me 1125 minus 975 upon 14. And that is 150 upon 14 centimeter. If you do the calculation here, turns out to be approximately 10.7 centimeter. So this is our final answer. The center of mass has shifted 10.7 centimeter to the left, and that is the distance moved by the boat. Obviously the entire boat moves to the left, but a distance of 10.7 centimeter. Let me repeat this concept one more time. We computed the initial center of mass as 975 upon 14 from one end. In the new situation, we computed the center of mass again from one end of the boat, and it was 1.25 upon 14. So the center of mass has actually shifted, left its original position and gone to the right. But according to the principle of conservation of linear momentum, center of mass does not change. So in order to keep the center of mass at the original position, the boat will move leftwards through a distance which is x2 minus x1, and that gives us the answer as 10.7 centimeter. This is part 1, by which we have used the concept of no shift in the center of mass. Now let us repeat the same problem using the conservation of momentum. One word of caution here is that when we use the conservation of linear momentum, we cannot work with relative velocities. We have to work with the velocities with respect to ground, that is with respect to the inertial or fixed frame of reference, and that is what we are going to do now. Let us consider that the ball is moving to the right with the velocity v1, and the girl is moving to the left with the velocity v2. Obviously, they are starting to move at the same time, and they are exchanging their positions exactly at the same time. So both the velocities must be same. Let the time required for the journey be t, so that I can define here v1 speed as distance upon time. At the same time, v2 also can be taken as distance upon time. Another word of caution that this equation, conservation of linear momentum, is a vector equation, and we have to consider the directions. Sense of direction is very important. So what we will do is, anything moving to the right we will take as positive, anything moving to the left we will take as negative. Let us assume that we do not know in which direction boat will move. So let us take that the boat moves forward with a speed Vb. If you get a negative answer, it means the speed of the boat is not to the right but to the left. But please note one more thing, that an unknown quantity we must not put a sign beforehand. The sign of the unknown quantity will automatically adjust itself and will give us a proper sense of direction. So let us take the velocity Vb to the right. Now these v1 and v2 are the velocities with which the boy and the girl are moving on the boat. So these are the relative velocities. When we come to frame of reference problems, when the frame of reference is moving, one very important principle which you must remember is this. The velocity with respect to ground is the velocity which is relative plus relative to frame of reference plus the velocity of frame of reference itself. This can be proved very easily, but you can understand it. It's a very simple fact that velocity with respect to ground is the relative velocity with which the body is moving plus the velocity with which the frame of reference is moving. So let me take v1a as the actual velocity of the boy, and that will be v1 plus vb. At the same time, v2a, which is the actual velocity of the girl, let me take it as v2 actual is the velocity of girl. Please note that it is to the left, so it will be minus v2, and we have taken the velocity of boat to the right anyway, so plus vb. When we use the principle of conservation of linear momentum, we cannot use v1 and v2, which are the linear velocities, but we have to use v1a and v2a, which are the actual velocities. Now we are going to apply the conservation of momentum. Please note here, v1 and v2 relative velocities we have already computed as distance upon time, that is 1.5 upon t and 1.5 upon t. T is constant, time is not relative. So whatever time boy takes to reach to the girl, same time girl takes to reach to this position. So the velocities are same, but of course in the opposite directions. What was the momentum before all this process began? Obviously it was 0. So the linear momentum afterwards, after the positions have been exchanged, must also be 0. So then we must equate it to. So the momentum before the process is 0. Let us find the momentum after the process. Please note again, linear momentum is a vector quantity. The one to the right will be taken as positive. The one to the left will be taken as negative. So what we have here is m1 into v1a plus m2 into v2a, where v1a and v2a are the actual velocities of boy and girl with respect to ground, plus, let me take the mass of the boat as capital M, into the actual velocity of the boat is v. Please note the difference again. v1a, v2a and v are the actual velocities of boy, girl and the boat as seen from the ground, whereas v1 and v2 are the velocities with which boy and girl are moving on the boat, so they are relative velocities. We have used this funda. Velocity with respect to ground is the relative velocity with respect to frame of reference plus velocity of frame of reference in order to get this. Now let me put these values over here and let us see what do I get. I get 0 is equal to m1 into v1a is v1 plus vb plus m2, what is v2a? It is minus v2 plus vb, and this we have taken as vb, plus m into velocity of v2. Let me rearrange the terms, and what I will get here is m1 v1 minus m2 v2 plus m1 vb plus m2 vb plus capital M vb is equal to 0. That is m1 v1 minus m2 v2 plus m1 plus m2 plus capital M, which is mass of the boat, into vb equal to 0. Now it is time to put in the values. Mass of the boy we have taken as m1, which is 60. Its velocity v1 is 1.5 upon t. Mass of the girl is 30. Her velocity is also 1.5 upon t. This is 60. Sorry, mass of the girl is 50. 60 plus mass of the girl 50 plus mass of the boat 30. And let us take velocity of boat as the distance moved by the boat in the same time t. This time t is not relative, it is going to remain same. So vb will be distance moved by the boat upon time, and this is equal to 0. As you can see, time will cancel and I will get 60 into 1.5, that is 90, minus 50 into 1.5, that is 75, plus 60 plus 50 plus 30 gives me 140. X is equal to 0. And now it is time to get our final answer. -90 minus 75 is 15 is equal to minus 140x. That gives me x as minus 15 upon 140. This is in meters, that is minus 1500 upon 140 centimeters. Again, you will see, if you remember, minus 150 upon 14 is what we got in the previous method, and the answer is 10.7 centimeter. The negative sign indicates that the boat has moved to the left. So we have seen both the methods. Number one, the method in which we said that center of mass does not move, and method 2 in which we have computed using the conservation of linear momentum. Two words of caution here. Number one, the linear momentum equation is a vector equation and must be used with proper signs. Caution number 2, the velocities must be with respect to ground and not relative velocities. So V1 and V2 we have actually converted in terms of V1A and V2A, which were the actual velocities as seen from the ground of the boy and the girl, and that we substituted here to obtain our final answer. Please note that time remains same. By the time boy moves and takes the position of the girl, in the same time girl moves and takes the position of the boy, in the same time t, the boat moves a distance x, and that gives us the final answer as minus 10.7. Advantage of this method is you can also get the velocity of boat if V1 and V2 are given to you, and if you are asked to find the velocity of boat, you can use this particular format and get the value of Vb. If only distance is asked, I think the center of mass not shifting or a funda is a much better, quicker and easier way out. Thank you very much.